Welcome to the Cold Steel Podcast, hosted by Amir Farouk and myself, Chad Ball. We consider it an absolute privilege to bring you guests from around the world who are truly experts in their craft. Our mission is to offer you a combination of not only masterclasses on clinical surgery topics, but also insights into achieving personal growth, productivity, and fulfillment as both a surgeon and perhaps more importantly, as a human. We're so excited today to welcome Dr. Paul McBeth to Cold Steel. Dr. McBeth is a critical care intensivist as well as a trauma and acute care surgeon. He's a clinical associate professor in the Department of Surgery. And what's particularly interesting about Dr. McBeth was his initial career as an engineer before entering medical school. We're absolutely thrilled to chat with him, as well as how his engineering background in particular colors and changes the way he views medicine in general. Tell us about where you grew up, how you trained, where you trained, and what that pathway looked like. Because, obviously you're not unique in blending engineering and medicine and surgery in particular, but it certainly is an uncommon pathway.
Sure, yeah. I grew up in Calgary, Alberta. I grew up in a family where my father was an engineer, and he was a civil engineer and worked in the oil and gas industry. And growing up as a child, we took on a lot of projects around the house, and so from a very young age, I was interested in design and building and construction, and spent a lot of time taking things apart and putting them back together. And so after growing up here in Calgary, I went to the University of Calgary. I did an undergraduate degree in mechanical engineering. And at the end of my training, a lot of my colleagues were working in the oil and gas industry, and I realized that just wasn't my thing. And at the time, I was interested in robotics and control systems. And so I ended up doing a master's in biomedical engineering at the University of British Columbia, where I worked with a team of research engineers developing tools for understanding how robots could be integrated into the operating theater.
And ultimately, what was it sort of that triggered you to sort of switch careers or jump ship and benefit us with your skills and your talents in surgery?
Yeah, so some of that research we were doing at the University of British Columbia, we wanted to have an understanding of how robots could be integrated into the operating room. And in order to understand that, we really need to characterize how a surgeon operates. And so at the time, what we did was we teamed up with a general surgeon, Dr. Alex Naj, who was doing a lot of work at the time in laparoscopic procedures. In fact, he was one of the founders of laparoscopic techniques in Canada. And what we wanted to do is we wanted to understand how he was operating and how he was manipulating his surgical instruments. And what we did was we equipped these optoelectronic sensors onto the tools that he was using in the operating room, as well as onto his torso. And we could calculate the movements of the surgical instruments as well as the postures that he was using to manipulate those instruments. And so from that, we could characterize the kinematic model of movement of a surgeon. And so this is important not only for how you would integrate this into the design of a robot system, but also in terms of characterization of surgical performance, how you evaluate new and improved instrumentation for the operating room as well. And so this was quite a novel approach to characterizing surgical performance, because at the time, a lot of evaluation techniques were based on subjective measures of performance. And so we completed this work, and then once I finished there, I ended up coming back to Calgary and approached a fellow named Dr. Garnet Sutherland, who was just starting a project called neuroArm. And this was a project that was in collaboration with MD Robotics, which is the company that developed the Canada-Arm for the space shuttle and the space station. And what we wanted to do is we wanted to incorporate technologies for space robotics into robotic systems that could be used in neurosurgical applications. And so the challenge here was that we had an intraoperative MRI system, which is a ceiling mounted magnet that would come in and out of the operating theater to generate images preoperatively, intraoperatively, and postoperatively. But as you can imagine, a magnet mounted to ceiling rails is a bit cumbersome. And so what we wanted to do is we wanted to design a robot system that could be deployed within the magnet and allow surgeons to operate in real time while images were being generated. And some of the challenges around this became, as you can imagine, operating in a very confined space within the bore of a magnet. As well, we had challenges with materials. The materials that we used to develop the robot system had to be compatible with the MRI. Not only the structure of the robot, but the actuators and sensors all needed to be MR compatible. So this presented a lot of challenges. And so I had the opportunity during that time to work with clinicians as well as engineers. And during that time, I developed an interest in medicine. And so I ended up applying to medical school and got accepted. And this turned into my career as a surgeon.
That's a really interesting story, Paul, and a really interesting history. You know, as you kind of describe, you sort of skirted around the edges of medicine and surgery in particular there for a number of years. And I think a lot of us know Garnet Sutherland. You know, he's a recipient of the Order of Canada. He's a Governor General's Innovation Award recipient as well. You know, he's an internationally renowned neurosurgeon. What was the actual trigger that pulled you into surgery? Number one, and number two, why not neurosurgery? Like how did you end up in general surgery and then eventually trauma and critical care?
Yeah, that's an interesting question. So during that time I was working as an engineer, I had a really unique job. I had the ability not only to be working directly with the engineers, but the office I had was right next to the operating theater. And so I would have the opportunity to come into and see surgeries and understand some of the limitations of the current surgical techniques that were being used in neurosurgery and try to identify what those challenges were and incorporate some engineering solutions to those challenges. And so it was a very unique job in the sense that I was based in the hospital. I wasn't based in an engineering lab or a facility outside of the hospital. And so it was really those interactions with the physicians that really drew me to pursue a career in medicine. And you know, a lot of people do ask me, why didn't I pursue a career in neurosurgery? And as I went through medical school, I continued some of my work with Garnet Sutherland. And, you know, you meet individuals along the way and you get pulled in different directions. And so one of the individuals I met early on was Dr. Andrew Kirkpatrick. And so I developed an interest in trauma and critical care. And so that's what really drew me in that direction. My interest in critical care really surrounds my interest in engineering. If you look at the human body and in critical care, we spend a lot of time thinking about the physiology of the human body. And this can be broken down into systems very similar to an engineering approach. In control systems work in engineering, we talk about negative feedback control systems. And if you really break down the human body, it's just simply a series of negative feedback control loops. And so this is what really drew my interest into critical care as well as into surgery.
Are there some other ways in which you kind of integrate your engineering mindset and things that you learned as an engineer into the way that either you practice as a general surgeon or a trauma surgeon or critical care physician, or the way that you think about research and all the innovative things that you do? Yeah,
one of the basic premises of engineering is understanding how a system works and defining it into very discrete components. And engineering is interesting that way, in that you can characterize the behavior of a system in a certain way. And engineering is very black and white that way. You can understand the behavior of a particular system. Your car drives down the road, you know how it's going to behave. What's different in medicine is that instead of problems being particularly black and white, it seems to be all different shades of gray. And there's a lot more variability in the human body. It's more difficult to predict how things are going to behave. And so it does add a series of challenges in a way that is not a typical engineering system. And so this mindset of looking at particular problems, understanding the physiology, the pathophysiology, I think is really important. And as an engineer, this way of thinking of defining problems, understanding the basic principles of either anatomy, the pathophysiology of a particular illness, I think really helps you understand how a patient responds to particular treatments and whether they're moving forward or not.
I think if you look at, really experienced high volume clinicians, whether it's on the surgical side or the physician non-surgeon side, they probably don't know that's what they're doing, quite honestly. But really the fundamentals are exactly what you've described in the engineering world, eh?
Yeah, it's true. And as you evolve through your training and experience, you become more accustomed to seeing those types of problems and being able to come up with solutions to those problems. And in engineering is very similar. As you become more experienced with different engineering principles, those solutions come to the surface much more quickly.
Can you talk to us a little bit about specifically what is bioengineering, and are there some specific things that characterize bioengineering that set it apart from other disciplines of engineering?
Yeah, bioengineering is a very broad topic. It's in the field of biomedical engineering, there's components in mechanical engineering, electrical, computer science. And so it brings together many different areas of engineering to solve particular problems that are related to medicine. My background is in mechanical engineering, but I've done a lot of work in electrical engineering as well. And combining those two disciplines to solve challenges in medicine. There's here at the University of Calgary, we have a very strong group in material science related to biomedical engineering, specific when it comes to orthopedics and joints. And so this group is being led by a number of individuals that have experience in mechanical engineering as well as civil engineering, where we're looking at understanding the behavior of tissues under different loading conditions. And so you can imagine that these areas of engineering can cross many different areas of engineering to solve particular problems in medicine.
Yeah, that's such an interesting outlook and skill set to be able to break down these problems into their components and their controls and then build them back up, Paul. One of the interesting things I think that a lot of us in Calgary got to do was quietly watch you work away when the initial waves of COVID hit, in terms of generating or creating a novel engineering solution to the perceived or at that time highly concerned for a lack of ventilators. Could you tell our audience a little bit about what that process was like, how it felt, maybe most importantly at that time, whether was that concern, which maybe did or didn't pan out, but certainly was a concern. And then maybe equally importantly, how do you break that problem down as an engineer and then move forward in an expedient and efficient and relevant time frame?
Yeah, that was a very interesting project. And it got started early on in the pandemic where there was a perceived need for additional support for mechanical ventilation. And this really came out from the experience that the Italians had early on in the pandemic. And there was a group of engineers, both at the University of Calgary and at the University of Alberta, who had expressed interest in helping to develop ventilators to support the healthcare system. And these groups had approached Alberta Health Services to see if they could make some contributions. And one of my colleagues in the Department of Critical Care Medicine asked if I would help work with these engineers, knowing that I had some experience in both engineering as well as critical care. And so it was really interesting working with these engineers right from the beginning. There were a variety of concepts that had come to the surface about how to ventilate these patients with COVID. And our traditional approaches to ventilation in the ICU are based on positive pressure ventilation, where a patient has an endotracheal tube and is under a system where positive pressure is administered through that endotracheal tube. And one of the engineering teams had actually come up with a very unique design that was based on a negative pressure ventilation system, very similar to the iron lung that had been developed for the polio pandemic 50 years prior. And so we worked with the engineering groups, and it became obvious that some of these solutions that were being proposed would work and some of them would not work. And so we had to focus our efforts in identifying solutions that would work. And the other very unique aspect of this was the amount of support that came from the community. Here in Calgary, we have a predominantly energy-based economy, and there's a lot of highly skilled technicians, engineers who work in the oil and gas industry. And there were a number of companies that came forward and said, we have these services to offer. How can we help? Solve this problem of ventilators? And so we started working together with companies that were building components for the oil and gas industry, and we turned around and developed prototypes that could be used to help ventilate patients in the intensive care unit. And so one of these examples is a company named Spartan Controls, and they develop control systems and valves for oil and gas industry. And so we started working with them and identified what the requirements were for the ventilator. We needed to have an understanding of what types of pressures needed to be delivered to a patient. We had to have an understanding of what the limits of the system had to be, what kind of control feedback mechanisms had to be in place, what kind of alarms need to happen to alert the care providers that there were problems within the system. And so within the course of about 3 or 4 weeks, we had gone from an idea on a napkin essentially to a fully developed prototype, essentially made out of components that were really meant to be used in the oil and gas industry. And it was really a unique experience in the sense of how quickly we came together, how we developed this design, and how people from the community really teamed together to come up with a solution to a problem that was facing our communities. And so it's a very unique opportunity. And one of the things that we also did was we created an evaluation team. As we moved forward with this project, we found that there was a number of groups that were doing similar projects and developing ventilators. And so we wanted a way of testing and evaluating these devices so that if we did need them, that they could be used clinically. And so we developed a series of testing protocols to evaluate these devices to ensure their safety. And through work with Alberta Health Services, we evaluated about 7 or 8 designs over the course of about 2 months. And one of the groups here in Calgary, we received some additional funding and we got Health Canada approval for our prototype and manufactured 200 of these devices. And they were donated, to Alberta Health Services, and they're currently in a warehouse ready to be used in the case of an emergency. And fortunately, with the pandemic, we did not require their use, but they're available just in case. And one potential application would be the deployment of these systems in more remote or rural locations, either in Canada or abroad. And so they do have quite a bit of utility that way.
That was such a cool endeavor and voyage to watch, and I'm sure it was infinitely more exciting to be part of. So congratulations for that. You've given us, obviously the ventilator COVID example you just outlined. You've talked a little bit about robotic systems and not only neurosurgery and unique environments like intraoperative MRI, but also beyond that. What other areas of surgery come to mind when you think about the interaction and the integration of more formal engineering approaches into surgery? What gets you excited that's coming down the pipe, and maybe even as an area that's ripe for opportunity to explore for you?
Yeah, I think there's two really exciting areas. One is in the realm of patient safety, and the other is in the realm of training. So when it comes to patient safety, I think there's a lot of potential opportunity for us to look at ways in which we can better function to ensure safety of patients and to improve their outcomes. And whether this is through black box devices that have been deployed in other areas where you have monitoring of various components in the operating room, or simply for the design of new devices that are being put into patients, whether they're implants or processes in which improve the efficiency and safety of the patient. So I think this is an area that's really exciting. The other area that I think is evolving is in the realm of training our trainees. And this is particularly relevant as we're seeing a very dramatic shift in the way we train our trainees, particularly around competency-based education. And the current methods of evaluation are really subjective and potentially unreliable at really providing meaningful feedback to our trainees. And so with the integration of engineering principles and technologies, very similar to what I described earlier with some of the work I had done in my master's, where we are looking at quantitatively evaluating the performance of an expert surgeon using kinematic measures, we could potentially do the same thing, but do it on a much broader scale, where we could evaluate residents and their performance in the operating room and provide very specific targeted advice on how to improve their surgical technique. And not only could that be used in our trainees, but it could also be used for some of our more senior surgeons in order to quantify their techniques and use that as a guide for our trainees as well. And so I think this is an area where there's a lot of potential for further development, particularly as our resident work hours change and we need to become more focused on how we create an experience for them that's very targeted at helping improve their performance. And so I think this is an area that is really at the precipice of growth here.
Paul, how do you interact with physicians, administrators, sometimes politicians, maybe, who work or work within healthcare, or certainly have a portfolio that manages healthcare, that don't have the same very tactical engineering component-based mindset as you when you're trying to solve a particular problem? How do you try and communicate the relevance of these engineering type approaches, these foundational elements, to many of our colleagues, myself included in that, in medicine and surgery, who may not be naturally intuitive to those concepts?
Yeah, I think it comes down to really trying to understand what the problem is that you're trying to solve, whether it's a particular problem in the operating theater, whether it's the flow of patients to the emergency department. It's really trying to step back, understand exactly what the problem is, try to characterize that in a way that can be communicated effectively, whether it's to an administrator, to your colleagues about a particular clinical problem, and trying to identify what those problems are, what are the components that are contributing to that particular problem, and trying to identify solutions that work with the system that's in place. And the healthcare system is incredibly complex, and so understanding some of those basic principles, I think, is really important to come up with solutions that are unique that can help us achieve some of those problems, or achieve some of those solutions. And so I think really stepping back and being able to fully characterize what those issues are, I think, is important as a means of communication to your colleagues.
So, Dr. McBeth, you've touched a number of times on the podcast about sort of the engineering mindset, where you really try to define the problem that you're trying to deal with. Tell me practically what that looks like for you. So, you're presented a problem like, something big or small, something big like, how do we define surgical performance? How do we measure it? Or something very specific, like how do we design a ventilator in a low-cost way or an efficient way? What practically, can you walk me through, what does that process look like for you? And I'll give you some context. So on the podcast, one of the things that I think Dr. Ball and I have been obsessed about is exploring different ways of thinking about different problems. So, we had Andrew Ibrahim, who's an architect, talk to us a little bit about design thinking. Which is I'm sure you're much more aware of that than perhaps we were. But there's all these just sort of different ways of tackling problems that perhaps we in medicine don't typically employ. So walk me through a little bit about how you approach a problem. What are the sort of the very practical things that you do? Like, do you get out a piece of paper and try to map things out? Talk to me a little bit about your process.
Yeah, so that's an interesting question, and I'll share with you an experience that I've had where I've been involved in mentoring undergraduate students in engineering. And so the problem that we identified in trauma care is that we often have patients that arrive in hospital, and we really have no idea what has happened to them before they arrive in hospital. And so the problem here is trying to get a better understanding of a patient's injury, the severity of injury before they arrive. And the classic example is that we get these pages when the patient comes in for trauma, and we're given just little pieces of information on the page that are generally is not that helpful. And so what we wanted to do is we wanted to have a better understanding of patients before they arrive in hospital and how we can better prepare for those patients. And so I took this problem to our engineering faculty, and they said, this is a great project for our undergraduate students. And so they have a senior design course, and every year what I do is I bring over some of these engineering students to the hospital, and I take them around the hospital, and I give them an idea of the work that we do on the clinical side. And so over the course of several years, I presented this problem to these students, and every year it seems I get a very unique project out of it. So the first year we did this project, the mechanical engineering students wanted to focus on solutions related to the spine board. So they wanted to create a spine board that was embedded with sensors that would measure different parameters of the patient. And then this evolved the following year into a project where some electrical engineers were refining some of the sensors that were being used. And then this got refined further where we started working with computer engineers to develop some of the algorithms for interpreting some of the data that was being collected from these sensors. And then this past year, we had a completely new group who developed these sensors that measure perfusion of a patient. So the idea is that these little stickers would be attached to a patient that would measure perfusion. They communicate over Bluetooth to a control module, and then the signals get sent to my cell phone as a care provider in the hospital. So I get information now about a patient before they even arrive in hospital, which is great because it gives you a lot of information about how sick they are, the need for a blood transfusion. Eventually, we hope to get there, the need for an operating theater. And so we go through a very systematic approach of identifying what the problem is and identifying what potential solutions are. And we're often constrained by the environment in which we work in. We are constrained by the physical infrastructure that we have, by the interactions we have with the patient. And so we need to have good understandings of those constraints, as this will often influence the design that evolves from trying to solve that particular clinical problem.
One of the, I think, the hallmarks of a good idea is that when you hear about it, it's like obvious to everybody that hears it that, of course, that is something that should exist. And that I like the spine board idea. Of course, that's something that should exist. But like, what is it that you think that's different about the perhaps that sort of mentality that allows you to see perhaps problems like that, whereas everyone else might have just said, like, I think, for example, there's all these debates in trauma literature and emergency department literature about, okay, well, who needs to wear a C-spine collar? Can we do it? Can an MRI or a CT be enough to clear them? Blah, blah, blah. The debates rage on. But, like a unique solution to some of these problems might be what you're talking about, like, a spine board where you can actually measure the pressure, or a collar that might measure the pressure. What do you think it's something about the training itself, or do you think it's the fact that perhaps these engineering students don't have all the sort of the baggage of the weight of all the previous history of research that's been done in these areas that allows them to see these unique solutions to these problems?
I think it's the latter. I'll give you an example of this. I mentioned earlier that one of the things I do is I bring these engineering students over to the hospital, and I show them around. I take them to the trauma bay, to the ICU, to the operating theaters, and basically immerse them in that clinical environment so they have an understanding of where we work as clinicians. And I also invite them to come with me when I'm on call. And we had one night where I had a couple of engineering students with me, and we had a level 1 trauma. And so the students came and they stood in the back, and we did our resuscitation. And afterwards, we did a little debrief. And it was really interesting to see the insight of one of the particular students. He said, Dr. McBeth, I did a little decomposition of the resuscitation. And I said, what do you mean? And he goes, well, I took out my watch and I timed different events. And so he went through and he said, it took you guys about 2 minutes to get the patient onto the emergency department stretcher. It took another 2 minutes to get the monitors on. It took you another minute or two to figure out what was going on, and then another minute to put in the chest tube. And it was really interesting to see what data points he kind of picked out during the resuscitation, and that every single point that he picked out was clinically relevant. And so it's interesting to see the mindset of engineering students, and particularly when they haven't had a lot of exposure to medicine. They look at a problem, they try and characterize it, and it's really interesting to see the solutions that they come up with, because often they're solutions that are directly relevant to what we're doing. And so it's creating that environment to allow them the opportunity to be immersed into the clinical world, I think is really important. And particularly around solving problems that are clinically relevant. You know, it's a challenge. If you're just working in a lab, you might be developing some type of widget. But if you're not working on the clinical side, that particular widget that might be developed may not have much clinical relevance. And so it's really important as clinicians that we do work with engineers in order to give them guidance as to what are clinically relevant problems that we're trying to solve.
I think one of the things that's sort of inherent in this process is the ability to adapt and to overcome failures, right? Because I'm sure the first prototype, the second prototype, the 100th prototype isn't the definitive final thing that you'll have to work with. What does that process look like from an engineering perspective in terms of iterating and dealing with failures?
Well, the design process is very iterative in its very nature. It's looking at a particular problem, identifying a solution, and that solution may not fit the entire picture in which you're trying to resolve a particular problem. And so, especially within the complexities of medicine, that process of iterative design is really important in order to come up with solutions that are effective, that integrate well into the clinical environment in which it's to be applied. And this is particularly important because no patient is exactly the same. And so you need to be able to adapt your design so that it has a broader application. And that design process involves understanding what that clinical problem is, developing a solution, testing, evaluating, going back, refining your design. And sometimes that process can take a while. But at the end of the day, it's very rewarding, and being able to work with the engineers to develop solutions to these problems is an exciting part of the work I do.
We're hoping to take you on just a very quick tangential route here and ask you a very specific question. So you obviously live in the realm of injury and trauma care, and you know, although ground level falls, quite honestly, and falls in general have become the dominant mechanism of polytrauma and major injury in blunt trauma centers across the world, motor vehicle crashes still represent a reasonably large a cohort or etiology of the injuries we treat. I'm curious what your sense of autopilot or auto drive or self-drive motor vehicle engineering is. I'm curious what you think that time frame is and what that feature looks like, because certainly, you know, all of us that work in a hospital system would love to see the end to motor vehicle crash related injury.
Yeah, that's a great question, Chad. If you look at motor vehicle injuries and motor vehicle design, it's changed dramatically over the last 20, 30 years. If you look at the way vehicles are designed, there's a lot of emphasis on safety features, whether it's airbags, crumple zones. You know, when I'm in the trauma bay, the paramedics will often show me a photo of the vehicle, and they all seem very surprised at how crushed the vehicle looks. But if from an engineering perspective, that's exactly the way it was designed. The vehicle is designed to take the impact and have crumple zones to absorb that energy so that the passenger or the driver is protected from that impact. So a lot of work has gone into engineering design of vehicles. But I think the next stage, as you allude to, is really around the autonomous functioning of vehicles. And there's a few limitations here. And one of those limitations is in the sensors, as well as the ability for vehicles to communicate with each other. With the 5G networks that are being rolled out, those communication between vehicles is going to become ubiquitous. So there can be high data transfers between vehicles to allow them to communicate. And the reason why this is important is because then you know the behavior of another vehicle, where it is, how it's moving, what velocity they're going at. And then the other aspect that's really important is the integration of sensors into vehicles. And so there's different types of sensors, radar, LiDAR cameras, which are devices that use laser to characterize the environment around them to allow them to know where vehicles are. Now, the environment in which a vehicle operates is incredibly complex. For example, you might be driving and you might see a person beside another vehicle, but you recognize that that person might dart out from behind the vehicle. So you're unconsciously making an assessment of where that person is and whether or not they're going to be potentially stepping out in front of your vehicle. While a computer system, they may recognize that there's a human being standing there, but they may not recognize where they might be going and being able to anticipate their movement. And so I think as sensors and computer power evolves, we're going to be able to solve some of these challenges. And I think it's a really exciting area, particularly around injury prevention related to motor vehicle crashes. And so I think this is a really exciting area that's going to be evolving, and we're going to see some dramatic changes probably in the next 5 to 10 years.
You've been listening to Cold Steel, the official podcast of the Canadian Journal of Surgery. If you like what you've heard, please leave us a review on iTunes. We'd love to hear your thoughts, comments, and feedback. So send us an email at podcast.cjs@gmail.com or tweet at us at CanJSurge. Thanks again.